Good afternoon, everyone. Welcome to the MetaMAT series of webinar. For today, it's my pleasure to introduce Professor David Bergman from the School of Physics and Astronomy from the University of Tel Aviv in Israel. So David is going to talk about scattering electromagnetic eigenstates of a two-constituent composite and their exploitation for calculating a physical field. So David, it's your turn.
Thank you. Okay, actually the title of my talk is a little shorter, but essentially what who was speaking before? Was it Muammer or Bogdan? Or
Muammer was speaking.
Muammer was speaking, very good. Okay, well, you can see the title of the shorter title of my talk here, so I'll start it right away. Here's a list of contents. First, I will review the electromagnetic eigenstates of a composite medium in the quasistatic regime. Then I will extend the discussion to eigenstates of the full Maxwell equations, namely in the non-quasistatic regime. Finally, there will be summary and some conclusions. Okay. First of all, we're talking about monochromatic electromagnetic fields. So there's a fixed real frequency, and the eigenstates are useful for calculating and understanding the electromagnetic properties of such a composite medium. In fact, I will be limited just to two-constituent composite medium. And first, I want to show a very simple example application. This is called either a superlens or a Vesilago lens, because it was invented by Victor Vesilago, then in the Soviet Union and way back in 1967. The idea is you have a single flat slab, which is an inclusion in an otherwise homogeneous medium. And what the special thing about it is that most of space is filled by a regular or normal physical medium, physical constituent. So it has a dielectric constant, which is greater than zero. It's real and positive. But the slab, intervening slab, has a dielectric constant, which is negative, real and negative. And in fact, it's equal to minus epsilon of the rest of space. Then what Vesilago showed or realized that if you have rays coming out of a point object, when they reach this first interface, they're of course refracted, but because of this negative value, the refractive index is actually -1, and therefore the refracted ray is on the same side of the normal as the incident ray. The two angles are the same. So in fact, all the rays, all rays coming out of this point-like object, they all come back and meet again at this point right here. And then they continue and they get refracted again, and again they meet at this single point here. So in fact, there are three focus points where the object is, here in the intermediate slab, and here I call this the image. And I call these regions, region 1 is where the image will be, region 3 is where the object will be, and region 2 is this intermediate slab. Now, without going into too many details, I'm just showing you that in this case, the eigenstates are very simple. In fact, it's a product of a two-dimensional plane wave in the xy plane times a somewhat more complicated function in the z direction, which is the perpendicular direction, and then you get exact expressions for the local electric potential in all three regions. here they are. They are one-dimensional integrals, which usually have to be calculated numerically, but in the special case, when epsilon1 is equal to minus epsilon2, and then this parameter s is equal exactly to 1/2. S and u are very important parameters. So when s is equal to 1/2, there are many terms, many factors here which vanish. The 2s minus 1 always vanishes, and then all these integrals can be calculated in closed form. And here are the answers in all three regions. And if you look at it, you see that in fact in all three regions, you get the Coulomb potential. If you started out from a point source, which was a point charge q, the only thing that you have to be careful about is the potential has exactly these forms only in those regions where it does not diverge. Because in fact, if you analyze these integrals carefully, there are regions where these integrals diverge. In fact, in region 1, which is the most interesting region, that's where the image is. In that region, s minus 1/2, as I said, s is exactly equal to 1/2 if epsilon1 is equal to minus epsilon2, but if it's not exact, but the imaginary part of epsilon is much less than the real part of epsilon, in both constituents, then this 2s minus 1 factor, which I said goes to 0, is the same as 2 times delta s, and it's approximately equal to this ratio. So if these two are very small, much smaller than this, the real part, then one finds that, in fact, in region number 1, if z is lower than the lower focus, then in fact the electric field is finite. If it's higher than the local focus, in fact, it goes like 1 over the sum of these two imaginary parts. So when they go to 0, it in fact diverges. Not only does it diverge, but if you calculate the rate of dissipation, which is equal in region number 1 to the imaginary part of epsilon 2 times the square of the field, what you will get is that if both of these vanish, in fact, this does not vanish. In fact, it tends to infinity. In fact, this divergence is fastest at the interface between regions 1 and 2. You see this here. I have marked an entire region where the result for E diverges. And you see that it's an entire region between these two focal points. Now, in fact, this is when the object is closer to the intermediate layer, closer than the thickness of that layer, which is L1. If it's further away than that thickness, in fact, there are not 3 focal points. There's only the point of the source, and then the intermediate focus becomes a virtual focal point. Then there's no divergence. But because of this divergence, as I said, the total dissipation rate also diverges whenever z lies between the 2 lower focal points. Those are in regions 1 and 2. However, as I just said, when z0 is further away from the slab than the thickness of the slab, it's only a virtual focal point, and so there's no possibility of perfect imaging, only of a narrower diverging beam of light rays, which you could see here. Whereas in the other case, we might think that maybe the image of a point source is also a point source. Things are slightly more complicated. So this shows you what you get when z0, where the object is further away in the thickness of the slab. And then what you get is that the rays that come out on the other side of the slab are diverging, but it is a narrower beam than from the object because it comes out of the virtual focus. Now, because all of the integrals I showed you, they're just one-dimensional integrals, there's no problem calculating them numerically. And this is something that a student of mine did. And he used epsilon 1 and epsilon 2 that were actually used in an experiment. And as you see here, Z0 is a little further, is a little larger than the thickness of the slab. And what you see here, you see this is the real and imaginary parts of the electric potential. This is the electric field squared, and this is the rate of dissipation. One more thing that is interesting, if instead of one point source, you have 2 point sources, at a distance of about 82 nanometers, and you look at E squared in the third, the first regime, below the slab. So here the two sources, one was here and the other was here, not here, but of course further up. And you see that in fact, you get a good separation between the images. The separation is 82 nanometers, even though the illumination here was assumed to be 365 nanometers. So in fact, the resolution is more than 4 times better than we would have expected from normal optical theory. The other thing that is important is that you see that the main places where you get a strong field squared is not at the is at the interface. Okay? Here's a slightly different case. Here, the Z0 is a little less than the distance between the two interfaces. And here you see again that you get an E squared, which is large. In fact, the strongest E squared is at the two interfaces, not at the 2 point focuses. You can see something similar also when you look at the resolution. You have 2 sources, 2 point sources. Now they are only 72 nanometers apart, but the illumination is still as before, 365. So you see, first of all, that there's a good separation between the images. And again, the maximum intensity is not at focal point, but at the interface. Here, the point source is even closer to the layer. It's less than half of L1. And here again, you see the electric potential and E squared. And here is the rate of dissipation. And you see that these things are large. The field and also the rate of dissipation, they are strongest at the interfaces, very close to the interfaces. And here is the resolution. And in fact, the resolution is good now even for a smaller object separation. In fact, what we learn from this is also that the closer the object is to the interface, the better the resolution, despite the impending divergence of dissipation. Now here it is, of course, not diverging because the 2 epsilons, epsilon 1 is not exactly equal to minus epsilon 2, but it's close. Finally, this is what my student Safahi did here, is he took those numbers that were used in experiment, epsilon 1 and epsilon 2, and also the thickness of the layer and everything, and the wavelength of illumination, and he made S minus half smaller than it really is. He made it 100 times smaller. And in that case, what you can see is that, in fact, the resolution becomes even better. You can resolve 2-point sources that are only 32 nanometers apart, which is less than 10 times smaller than the wavelength. This is the experiment that I mentioned a few times. In fact, it was done some years before this theory was done. There were other theories. And what they did here, they had a plane wave illuminating this system at 365 nanometers, was the wavelength. Then this was a quartz on one side. Then there was a thin layer of chromium in which grooves were placed, were drilled. In particular, the word nano was in this way. Then, so this is the source. Then PMMA, a layer of PMMA was the one side of the intermediate layer. The intermediate layer was silver. And then there was another dielectric, which was in fact photoresist. What is also important is that the PMMA layer was 40 nanometers thick, whereas the silver, which is the intermediate layer, is only 35 nanometers thick. So in fact, the source was further away from the important negative epsilon layer, was further away than the thickness of that layer. So in fact, we are back to this situation. So we expect to see an improved resolution, but it's all coming from a virtual focus. Here are the experimental results. So this nano grooves, this is a focused ion beam photograph of that nano. This is what was measured in the superlens, after the superlens. And this is what was measured in the same situation, but without the silver layer. And as you can see, you don't even have to measure anything very well. You can see that the resolution with the superlens is, of course, considerably better without the superlens. And here, when they measured on the letter A, you can see the red curve is without the superlens. The black curve is with the superlens. So you can see that the resolution is almost 4 times better with the superlens. Now, this situation was first treated theoretically by Pendry, who took Vasilago's idea, but instead of just using geometric optics, applied with wave theory to that. And he had to consider all the multiple scattering of the waves emitted by the point source, all the multiple scattering by the two interfaces. That's quite a complicated calculation, but he came out with a good result. The current analysis, which I showed you, avoids those complications by exploiting the fact that the eigenfunctions already take into account all the multiple scattering. Once you know the eigenfunctions, all the rest are simple calculations. In this case, the most complicated thing was to calculate one-dimensional integrals. There's also previous work by Milton and others that reached similar conclusions regarding the divergence of psi r and of the dissipation rate, after, again, a complicated analysis and after making various approximations. The current analysis, as I already said, is exact in the quasistatic regime and arrives at exact expressions for the electric potential. Those are valid for arbitrary values of S, namely for arbitrary values, complex values of the two dielectric constants. And as I said, numerical evaluation of those expressions, in the general case, only requires a one-dimensional numerical integration. As I showed you already, the best focusing is achieved when the imaginary part of S goes to 0 and the Z0 is as close as possible to the layer. Here are some summary and conclusions for the quasi-static regime. As I showed you, the application of the eigenstate approach enables exact calculation of the local electric potential created by a point charge in a two-constituent composite medium in the quasi-static limit. In the case of three parallel slabs, which I showed you, the microstructure, this analysis leads to an exact result, which is relevant for the possibility of achieving perfect imaging near any geometric optics focal point, when the imaginary parts of both epsilons tend to 0 and epsilon 1, which is equal to minus epsilon 2, is real. Now, the potential looks like that of a point charge, but only in a half space. What I mean by that is that here things diverge, but on the other side, it really looks like the other side of that focal point, it really looks like a Coulomb potential. And here too, below that focal point, it looks like a Coulomb potential. Here, it looks like a Coulomb potential all around the point source. Now, it has to be like that because Gauss's law is still valid, which means if you draw a sphere around one of these focal points and sum over all the normal components of the electric field over an entire sphere, here you will get the electric charge at this point. But at the other points, you have to get 0. There's no real electric charge, neither here nor there. The way it works is that although on one side is a Coulomb potential, on the other side it's much more complicated. It diverges, but even before it diverges, as you move around such a sphere, around the surface of such a sphere, the electrostatic potential oscillates between positive and negative values, and the oscillations get more and more violent as you approach this limit, but it does so in such a way that the integral vanishes. Here too, the integral, the normal component on a sphere or any other surface surrounding this focal point, that integral must vanish. As I said already before, when the imaginary part of the local epsilon tends to 0 everywhere, total dissipation can sometimes become infinite. And the basic mathematical reason behind that is that the point epsilon 1 of epsilon 2 equals -1 is a very singular point of Maxwell's equation. It is in fact an accumulation point of all the quasi-static eigenvalues, each of which is a pole of epsilon 1, is a pole of the macroscopic dielectric constant. Also, in the quasi-static treatment, there's no difference between the behavior of a TM wave and a TE wave. Finally, going beyond the quasi-static limit, the calculation of eigenstates has been done for a parallel slab structure. This article, which is a joint article with my student Asaf Farhi, application of that approach to a composite with a generic microstructure is discussed in this article, which came out a little more than a month ago, and was applied, in fact, in that article, an isolated sphere. Okay, now we're turning to the full Maxwell's equations, which are partial differential equations. Here they are. There are 4 equations. And they involve 2 fields, the electric field and the magnetic field. It's convenient to translate that into the first order partial differential equations. They can be translated to a second order partial differential equation for E, which can be rewritten in this form. There's a similar equation for H. So each one of these equations, these second order partial differential equations, is equivalent to the 4 Maxwell equations. And the things that depend on the system are, of course, the current, the external current, which is the source of the fields. And there are 4 material parameters here, V, U, T, and W, which are connected to ratios of the constituent parameters. First of all, kappa is just this combination of epsilon and sigma, the conductivity. Ki squared is just the wave number. In this case, it's the wave number in the number 2 constituent. Then you can write the local values of kappa and of 1 over mu using u and v and this theta function. Theta 1 is a step function which characterizes the microstructure. It's equal to 1 if r is inside the number 1 constituent and 0 otherwise. And here's a detailed definition of all these parameters. It's useful to remember that the u and t, both of them depend only on the electric permittivities of the 2 constituents, on the ratios. V and W depend only on the ratios of the magnetic permeabilities. Now, these are the full Maxwell's equations. If I'm looking for eigenstates, of course, I have to look at those equations where there's no external current. But even then, the equations become quite complicated because each one depends on 2 material parameters, T and W and V and U. And of course, they also depend on kappa 2, so this wave number. But because there are 2 parameters in each equation, this complicates life. So what the first thing I do is I make one of them 0. If I make mu1 equal to mu2, which means that the magnetic permeability is the same value in both constituents, then V, also W, vanish. In that case, the first eigenvalue equation, first eigenstate equation becomes this, because V is equal to 0. The second eigenstate equation, when I make W equal to 0, the second equation starts from the same equation, but I make U equal to 0, which means I make kappa 1 equal to kappa 2, and only the mu's are different. Then I get this equation. These are somewhat simpler, but still I have two types of eigenstates. I call them E and U and E and V, and these are the eigenvalues. But now it turns out that I don't have to solve both equations separately, because once I have solved the first equation and found, if I'm interested in eigenstates of the second equation, the E field is always connected to an H field. By this is one of Maxwell's equations, and therefore, if I've calculated EM of V, I can get it once I know HMW. HMW is, let's see, if U is equal to 0, and also T is equal to 0, because of these two relations. Therefore, once I know this HMW, I can calculate EMV. HMW satisfies the same kind of equation as EMU. See, because if T is equal to 0, then the equation, and J is equal to 0, then the equation for H looks just like the equation for E, and V vanishes. So in fact, HMW is the same, exactly the same as EMU, which means that I can write EMV as this constant times the curl of EMU. So I don't have to make a separate calculation of this eigenfunction. And the eigenvalue is what? Well, the eigenvalue is the same as the eigenvalue Wm. Sorry, the eigenvalue is Vm. Vm is related to Wm over Wm minus 1, and that is the same as Um over Um minus 1. So in fact, once I've calculated these eigenfunctions and eigenvalues, it's very easy to get all the other eigenfunctions and their eigenvalues. The only other thing that is important to keep in mind, because I want to use these eigenfunctions to expand the physical field, I need to have a scalar product. The scalar product is usually defined in this way: a product of two functions integrated only over the volume of the V1, only over the V1 subvolume. And this is a scalar product without complex conjugation. And this works even if the subvolume is infinite. So in fact, it's easy to get that that eigenstates of this type are orthogonal whenever the two eigenvalues differ. By contrast, if you look at the other type of eigenfunctions, E and V, then they are not orthogonal according to this definition. They are orthogonal according to a different definition. This has to be the definition. Okay, now the first application is to restrict myself to the case where magnetic permeability is the same value everywhere. And then I can write the electric field as the sum of an incident field and a scattered field. The incident field is just a solution of a simple Maxwell's equation where there's no microstructure. It's an entirely uniform medium with the moduli of the number 2 constituent, and you have the current here. Yes, I didn't write this here, but I'm assuming here also that Jx is non-zero only in V2. So only inside the number 2 constituent, and in that case gets the following expression for the scattered field. It's a sum over the eigenstates E and U, And there are integrals here of each of these eigenstates multiplied by the external current. And that is one way to calculate the scattered field. The other way is if you know the incident field is zero, this is another expression. In fact, the second expression is applicable even if we only know the incident field and not its source. This was in fact applied in the recently published article to calculate the scattering of a plane wave, incident plane wave, by an isolated sphere. This can be compared with some well-known results for that, which are shown and derived in the textbook by Jackson. Another thing that is possible to do, what happens if you have, instead of just one inclusion, you have a cluster of non-overlapping inclusions. In that case, you can write the step function. Theta 1 is a sum of step functions. For each one is for a different inclusion. And then the eigenvalue equation for those eigenfunctions is this one, where here you have, instead of theta 1, you have the theta of that inclusion. And then one can expand the incident field in those eigenfunctions, the scattered field in those eigenfunctions, but of course the scattering works only inside the volume of that inclusion, because only there these eigenfunctions, they're all divergence free. They're divergence free everywhere, but the fields E0 and also E scattered, they're divergence free only inside the VA, or inside the subvolume of the number one constituent. But then if one uses these expansions in the eigenvalue equation, in the equation for E scattered, one gets the following relation which connects between these scalar products and these scalar products. Now this is actually an infinite system of linear algebraic equations, inhomogeneous, for these scalar products, because this is the unknown. This is known because if we know E0, then we can calculate this. And in fact, the matrix which appears here is a symmetric matrix. It's given by these products. It's given by these products scalar products of an eigenfunction of one sphere, an of one inclusion, an eigenfunction of another inclusion. The integral is an overlap integral, but it's calculated only, integration is only over the volume of one of the particles. So you have to know these eigenfunctions not only inside the particle, but also outside the particle. Then you can calculate all the elements of this matrix. It's an infinite matrix, but it's a discrete infinite matrix, so it can be used to calculate all of these scalar products. And once you know these scalar products, you can calculate the scattered field. This is especially useful if all the inclusions have similar simple shapes. For example, if they're all spheres, In that case, the isolated inclusion eigenstates have closed form expressions, and so do the interaction integrals, the overlap integrals between eigenstates of different spheres. And this works especially well when the different inclusions form a periodic lattice. Okay, how can we now extend this to use the eigenstates to calculate the local physical field when the two magnetic permeabilities of the constituents are different? We still assume that the current density is non-zero only outside the V1 subvolume. It follows that the local physical field is also divergence-free outside that subvolume, just like the two sets of eigenstates. We can therefore expand the physical field in two ways using the two sets of eigenstates. This is one expansion. This is the other expansion using the E and V eigenstates. Now, if one substitutes this into the equation, into the Maxwell equation, one gets and multiplies on the left with these eigenfunctions, E and U, or also E and V, and gets the following two systems of inhomogeneous linear algebraic equations for these expansion coefficients. This is a system of equations for the A coefficients. This is for the B coefficients. This is the inhomogeneous term. And what one has to do is solve these equations. It's an infinite set of equations, but with the matrix, which is infinite but discrete. And using these expansions, substituting them into the Maxwell equation for E, the second order partial differential equation, we get the following equation. Now, what you can see here is that what is in these large square brackets is in fact E0. The incident field is the solution of the last equation in a uniform medium, namely, it's this equation. In fact, once we have solved the equation to get this field in a uniform medium, we get the expression for E. It's E0 plus all the rest. And the rest is, of course, the scattered field. Now, here we assume that this current was non-zero only outside V1. If, on the other hand, this current is non-zero only inside V1, then we switch the roles of the two subvolumes and repeat this entire discussion. Then if Jx is non-zero in both subvolumes, we separate the problem into two independent problems and finally recombine the two results of the physical field. Well, summary and some conclusions. I showed you how a theory, I developed a theory for calculating the monochromatic local electric field in a two-constituent composite medium created by a current density distribution or an incident field as an expansion in a series of two sets of monochromatic eigenstates of the full Maxwell equations. This leads to a relatively simple approach to the analysis of such a composite, where you can have arbitrary values for all of these physical parameters. In the case of a three parallel slabs microstructure in the quasistatic regime, which I talked about at the beginning, this leads to closed form expressions for the eigenstates, the discrete sum of one-dimensional integrals for the local field, which usually need to be computed numerically. This has already been applied to analyze the enhanced resolution for the Sulago lens with the magnetic permeability equals 1 everywhere, and this was done also away from the quasi-static regime. In the non-quasi-static regime, the new eigenstates will soon be applied to some more difficult problems. As I explained before, we know how to calculate the eigenstates of an isolated sphere. In fact, the eigenfunctions we know in closed form, what still has to be calculated numerically if we're not in the quasi-static regime, are the eigenvalues. We also have, there are also closed form expressions for the interactions, for the overlap intervals between eigenstates of two separate spheres. Well, I want to tell you who my collaborators were on some of his work. It was David Stroud from the Ohio State University in Columbus, Ohio. Saf Hatchi, who did his PhD under my supervision, is now a postdoc at Creel. Ari Chen is a postdoc at Ben-Gurion University in Israel. Yonatan Sivan was a professor at Ben-Gurion University in Israel. I say that the way that my spoken English is translated into printed English is not always perfect. But that's okay. I hope that the combination of the two enables you to follow.
It was a perfect. Thank you very much, Professor Bergman, for this very nice talk. And now we have time for questions.